kinetic energy a little bit. We're going to calculate potential energy to position and describe conservative and non-conservative forces, which we're going to have like a whole section on later. So there are two different types of forces, conservative and non-conservative. Conservative is like how it sounds. Basically, it's all the energy that you put into it can be recovered. So none of it is lost. It is all recoverable. And this is basically conservative energy is potential energy. Then we have non-conservative, and that is where the forces that are involved with it, generally they take some of that energy out that can't be recovered. This happens with like heat. You can't really recover a lot of energy from heat, not at least 100% of it. And friction causes heat, so you rub your hands together, that kinetic energy is turned into friction and lost through heat. Sorry, not turned into friction. It's turned into heat because of friction.
Basically, by harnessing one power, we're harnessing heat when you think about it.
Well, you are, let's see, heat is causing the molecules to move like low and high and low pressure systems, so yes, in a roundabout way, but it is not 100% effective, right?
So heat causes motion.
No, motion can cause heat. And in that case, motion was causing energy, and then you can turn it into heat.
Okay.
So it's like motion into heat. Heat, I guess, could cause motion if you're talking about pressure systems and like weather.
I was talking about like a solid, liquid, and gas.
Heat could, yes, heat can cause motion that way. If you're thinking of kinetic energy as temperature,
okay.
Yes.
Or on a molecular level.
Yes, on a molecular level. That's what we're talking about, temperature. So yes, that's fine. Just it's probably my dentist reminding me I have an appointment tomorrow.
Oh, that's every day. I was listening, I'm just like, wow.
Yes.
Oh, by the way, you have a dentist appointment tomorrow.
Thank you.
In case you will.
Yes. And a reminder like every day from them. I think they want me to go. Okay, so non-conservative forces. The blue path here is shorter than the red path. That means that the red path is actually going to lose more energy since it has a longer path. So non-conservative forces, it does depend on their path. Because in this case, it loses more energy because it's hitting more of the surface and it's going to dissipate more heat. Where here, it's not going to take out as much friction. So even though the displacement from A to D is the same, the path changes that energy. So in this case, non-conservative forces, the path is important. And you're going to see with conservative forces, the path will not be. So non-conservative, path, conservative, no path. Only position.
Oh, wait, what?
For non-conservative forces, like friction, for friction, the path matters. The longer you have your path, even if you start and end in the same spot, the more energy you're going to lose because you lose more energy through that friction because the friction is touching lots of different things. Whereas if you have a short path, the friction is only lasts from here to here, so it's not losing as much energy. So conservative forces are the exact opposite. It doesn't really matter what path you take. And things like conservative forces, like gravity, we can use as conservative. Spring force, electromagnetic forces, these things, the energy is all recoverable. And in this case, the path doesn't matter. So gravitational potential energy is just based on height. Something that's this high has more potential energy than something that's this high. And it doesn't matter if the object goes from here to here, so from the highest point and drops down, or from the highest point and then ends up falling all the way over here. It doesn't matter that it takes longer path to get there. It had this much energy, and now it has this much energy. It doesn't matter if it went from here to here or from here to here. The path will not matter. Only for that potential energy. It does in the long run because of air resistance and all that, but usually we ignore that for right now.
Come up with this. You can't see the red, but I can just flip it.
That's fine.
Oh, real recording right now, right? Oh, cool.
Okay, potential energy. It depends on the position of the object. So something with a higher position is going to have more energy than something with a lower position. What's interesting about potential energy is that you can make it negative. Right? With kinetic energy, we couldn't make it negative because the V was squared. So even if it was negative V, you end up with a positive V because 1/2 mv squared. But with position, let's say this is a really tall building and our duct is up here and the duct falls. So let's say that this is some sort of, I don't know, like 100 joules of potential energy. And when it hits here, now it has 0 joules. Well, let's say that there's actually a pit in the ground. And down here, now it could have like a negative 100 joules because of its location, just because we decided that right here was 0. So it is possible to have negative. What's important is that the change in energy here is 100 from here to here. So let's say A. And then from here to here, let's say B, is still a change in 100, this case. So from this part, let's call this initial to final position, it had a change in 200 joules. Well, that's what's important, is the change in, not necessarily the position.
I want to get tape because it's annoying having gravity. Tape with
Then I won't be able to put it away as easy.
Well, you can put it on top.
Now, potential energy in general is stored potential energy. Gravitational potential energy is where its position is mattering. So the gravitational potential energy is related usually to the surface of the Earth, but there are some cases where the surface of the Earth is going to be like a pit or it goes into the ocean or whatever, and you can still have negatives. That's fine. You could, if you wanted just to make your math really easy, you could define this, the bottom of the pit, as 0 instead. Just to make it a little easier, then you don't have to worry about negatives. But in the end, it shouldn't matter because usually we're looking at the change. The object interacts with the Earth's gravitational force, and so the higher up you go, the less gravitational pull from the Earth you're going to feel. So we actually end up with some interesting equations for this. It's like the potential energy is equal to m over r squared or something like that. G m over r. I don't know, I have to look that one up. But you can actually tell its gravitational potential energy depending on how close it is to the Earth as it goes up. Potential energy of this gravitational potential energy is going to be the Earth object system. So you're kind of including the object in the Earth, but don't worry about that too much. It's kind of meant to confuse you. We can just say this object kind of has this much potential energy. So enough theory, let's get into the math of this. Potential energy, which your book uses as PE. If you go up into physics in college, they'll actually use capital U because we use P for a lot of things. We use it for power, we use it for pressure, we use it for momentum. So they use it as U, capital U. And it's equal to mgy, or more commonly seen as mgh, H for height. I use y here because y as a displacement in the up-down direction is more going with the kinematic stuff that we learned. Yes.
So why don't you just use U in this class?
I use both.
Oh.
Your book uses PE, though, so that's why I kind of stuck with what your book was doing.
So the book's stupid.
You know, a little bit. It's written by smart people that don't have to teach. All right. Since gravitational potential energy is a type of energy, it is measured in joules. And on the right there, we can see that its initial height is final height. If this is final spot, that's initial spot. This is going to be the change in y. So if you put your change in y here times mass times gravity, you're going to get your potential energy. Should be super, super easy.
So is it delta y or is it?
Well, if you're looking at the potential energy at that location, it's y. If you're looking for the change in potential energy, then it's the change delta y. So our work kinetic energy theorem extended. We know that the change in energy, which is work, a transfer of energy is work, equals the kinetic energy, basically the change in kinetic energy, right? Kinetic final minus kinetic initial. Well, we can include that into our potential energy as well. If we look at this, for a conservative system, our initial energy equals our final energy. That's how I like to look at it. What's up there is going to be okay, but I like this better. Conservative system. Is there friction? No. No friction, no air resistance, then conservative. If this is so, the kinetic initial plus the potential initial should equal the kinetic final plus the potential final. Yes?
Why do we use W to represent friction?
W is work, and that's a transfer of energy out of the system or into the system. Friction transfers energy out of the system. Which, if there is friction, or some sort of transfer out of the system or into the system, like you're pushing on the duct and your system is only the duct, that would be you putting energy into the duct, so that could be some work. Or there's friction on the duct, or there's air resistance on the duct. Anytime you have that, the duct, the object losing energy or gaining energy, then work is done. That would be a non-conserved system. In non-conserved system, you're going to have basically your work is going to be your change in energy. This work is the transfer of energy. That is an energy. There we go. So the work, which is FD cosine theta of whatever the force is that's doing that work, it could be you pushing on the duct, so it would be that force that you apply to the duct, and then the angle between which way the duct is moving and the angle that you're pushing on it. Or it could be friction, right? Friction's acting in the opposite direction, so that would be 180, and then whatever the frictional force is. In the change in energy side, it's going to be basically kinetic plus potential final minus kinetic initial plus potential initial of that. So final minus initial. Final energy minus initial energy. And if you want to expand this a little bit, maybe you could do that as well. Now, there's lots of different types of energy, which we didn't really talk about here. We're just talking about energy due to movement and potential energy. Those are our mechanics stuff. But there's heat energy, which is Q. There's chemical energy, which, depending on the chemical, has its own symbol. There's electromagnetic energy, which is E, I think. There is one. I can't remember. So they have different ones. Right. Isaiah, are you? Yes, no. And then Mike's still writing. Good. Okay, there we go. So, with this potential energies, you can see that as it moves, A is going to have more potential energy if the reference point is the floor, or is the desk, sorry. B is going to have more potential energy than A if the reference point is basically it can fall down to the floor instead of the desk. So if you're looking at the change in potential energy that A could have versus B, or C, which can have even more since it's outside the window and can drop all the way down to the floor. So A has more potential energy than B than C because of where it can fall to. And basically we can say the difference is even though it has the same height, it has this different final positions that it can fall to. Yes.
I'm sorry. Oh wait, never mind.
You got it?
Yeah.
Okay.
Wait, I thought B would have more potential energy than A.
Yeah, they will.
Okay.
Yes. C has more than B, and B has more than A.
Yeah.
Because A can only fall to the desk.
Yes.
B can fall to the floor, and
And
C
C.
can fall all the way to the ground. So even though they have the same height, their final position is different, so that would be the different potential
in the
energy.
window that it is, the fact that it folds in like that, it's kind of hard to drop the book in there unless you were on the roof. But you
Okay, when you're trying to solve these things, you want to define your system. What are you looking at? If you're talking about the energy of the duct, then you're just going to look at the duct. If you're looking at like the duct, what am I thinking? The duct table system, then basically as the duct moves down to here, and there's no air resistance for defending, it's a vacuum in here, we can't breathe. The duct table system has a loss of no energy, so it's a conservative system. So you're looking at the duct table system, no longer just the duct. You're starting to think big picture. So define the system. If only conservative forces are present, this will mean that no work is done. So if the duct starts up here, and that's initial, and final is the table, then from initial to final, and there's no air resistance, it's going to be conservative. Because no work was done, no work was taken in or out of the system. In that case, you're going to look at energy initial equals energy final. In that case, kinetic energy is going to be 0 up here. And down here, potential energy will be 0. So you can find how fast the duct is going right before it hits the table. But once it hits the table, then work is done. Because the force of it hits with the force, and the force of the table hits it, and energy is transferred out of the system. Okay, so select the location of 0. In this case, you could either start 0 up here at the duct or down here at the table. Whatever you do, you need to keep it 0, that point 0 all the time. You can't say that it's up here 0 initially and then down here 0 finally. That would mean that it didn't do anything in between, even though we know it did. So usually the lowest point is 0 just to make your math a little bit easier, but it doesn't always happen. Identify the 2 points the object of interest moves. So the top would be initial, the bottom would be final. Sometimes, like roller coaster problems, which they like to talk about, it kind of has a couple of different points, like A, B, and C. So sometimes initial and final aren't enough points to really help you. So you could call it A, B, and C, or point 1, 2, and 3. The last little part, after you've decided on your equation and your orientation or your system reference points, apply the conservation of energy or non-conservative energy. If it has friction, you use this instead of the conservative. And then you're just plugging your values and should be able to substitute for the unknown. Now, this sounds like it's easy, one step, but sometimes it's a little difficult. Like, for instance, if you do have friction, especially if it's like on an inclined plane, then you have to go through, because friction is mu Fn, and this would be mg sine theta, or cosine theta, and this is Fn, so now you've got to go and find Fn by using the sum of the forces equals ma in the y direction. This is just like that. So then you have Fn minus mg cosine theta equals 0, and Fn is equal to mg cosine theta. So that will give you Fn, then you plug in here, find frictional force, and then once you find the frictional force, then you can plug it in there. So sometimes, in order to find these things, you're going to have to do a little bit of a roundabout way of finding it. just like here, if you have kinetic energy as 1/2 mv squared, and they're giving you stuff like displacement and acceleration and time, then you're going to have to use the displacement formula in order to solve for your velocities. So you're still going to have to use that other stuff that you learned earlier. Might be a little tricky. So even though it's a nice, simple, easy equation, you're still using everything that you've learned up to so far. With non-conservative forces, basically you're going to use the full work energy theorem, and that is just putting work into your equation, your change in energy equations. Basically you use everything else will be the same. You just decide, does it have friction? Does it have air resistance? A lot of the times, if it doesn't say there's friction or if it doesn't say there's air resistance, you can assume that there is either none or it's negligible. The only times you can assume that there's friction most of the time is if it says so. So if it says a frictionless inclined plane, no friction. If it says it's free fall, pretty much no friction.
What about air resistance?
Air resistance would be told to you. It would be say with air resistance. But if it says free fall, then you say no air resistance unless it specifically says it.
Oh yeah, and didn't you say we were calculating this in this chapter? Air resistance?
Yes. Okay. I mean, that's what you did in your coffee filter labs.
We didn't do that.
You guys didn't do the coffee filter lab? Maybe that's what we're doing here. Okay, I'll figure it out. Okay. Here's an example of energy conservation for you. I know this is what you were all waiting for a little bit. The last 10 minutes. An example. Your favorite. Okay. So a 600 kilogram roller coaster, that's a cart, roller coaster cart, starts at a height of 80 meters, rolls down to a height of 10 meters, and then back up to 30 meters again. Because it rolled past 30 meters. Assume there's no friction. What's the velocity at 10 meters and what is the velocity at 30 meters? Then we're going to say that it does have friction, and that friction is only 0.2. You want to know what would the velocity be at 10 and what would the velocity be at 30. So for A and B, let me draw a picture first. We have a roller coaster cart where its kilograms is 600. Ooh, that is bad physics. Bad physics. Mass is 600 kilograms. There we go. Okay. It starts at 80 meters. It rolls down to, let's do this a little better. There we go, 80. This is 10, and this is 30. Yes.
Okay, wait. So the roller coaster is essentially on an inclined plane.
It is.
Supposed to work. So how are we supposed to calculate it without data?
Energy. That's why energy is so much better. Because it's so much easier. We're going to look at, for A and B, is this a conservative system or a non-conservative system?
Conservative.
Why is it conservative?
Because it believes in strong economic policies.
We're going to go with Gianna's answer, no friction. Okay, so it's conservative. Which means that the initial energy is going to equal the final energy. In other words, at point A, the energy is going to be the same as at point B, which is going to be the same at point C. What type of energy does it have at A? Potential energy, due to gravity, right? At B, what type of energy or energies does it have?
Kinetic.
Kinetic and potential. And how about at C, what kind of energy does it have?
Kinetic and potential.
Kinetic and potential.
I mean, if the roller coaster works.
Right. If it's, conserved. Okay, so now we can find the energy at A by doing the potential gravitational energy at A. So what's the equation for that? mgy or mgh, however you want to do it. Mgh, mgy. So let's plug that in. Energy at A is going to be 600 times 9.8 times 80. And this is going to give us some big numbers. 4.7 times 10 to the 5 joules.
I don't think that's safe.
What energy initial equals energy function?
I did, yes.
Oh,
And
that's
since
a high roller coaster.
hey, don't make fun of my problems.
I'm not making fun of it because I'm scared.
So, why does initial equal final? No friction, no work done on the system. No, there's no air resistance. This is the amount of energy at A. Does not answer the question.
Okay.
Okay, so how much energy is going to have at B?
The same amount.
The same thing, right? And how much energy is going to have at C? Okay, so if we know that energy B is 4.7 times 10 to the 5, and we know that it's made up of some kinetic and some potential, how are we going to find the velocity?
Using our equations.
Equations. What equation should I put down here? How about, we'll start with EB is made up of some sort of kinetic energy at B plus some sort of potential energy at B. So EB we know is 4.7 times 10 to the 5 because it's the same as EA. Then kinetic energy is going to be 1/2 m and v squared at B plus mg, and the height at either y or we'll call it y at B. It doesn't matter. This could be hb too if you prefer. And now we just plug our numbers in. So this is 4.7 times 10 to the 5, 1/2 times 600 VB squared plus 600 times 9.8 times 10. We should be able to solve for BB. We can do the same thing for EC, but in the interest of time, since we only have 5 minutes, I want to go over the friction one too. So, sorry to kind of cut this short, but frictional coefficient is 0.2. What type of system is C and D in? Conservative or non-conservative? Non-conservative. There is friction. So, non-conservative. In a non-conservative, we're going to use the same picture. What equation are we going to use?
Change in E equals work.
Okay, work equals the change in energy. So as we go from, basically, the work done is going to be the frictional force, is going to be equal to the change in energy, which will be B, right, kinetic at B, potential at B, minus the energy at A, which is just the potential at A. This work is going to be the frictional force on FD cosine theta. And this is going to be 1/2 mVB squared plus mg h at B, or y at B, minus mg h at A. So this is always opposite direction in which it went, And you're right, this distance is going to be a little tricky since it is an angle. It depends. Did it drop or was it, straight? What is the angle? So in this case, they'd have to tell us, which they didn't here because I wrote the question and wasn't thinking about it. But otherwise, I have to give you some sort of D in order for you to solve for this.
Come out to the softball field ready to practice. Please
Oh, the
bring
D
all
from
cords and
A
gloves.
to
Yeah, I have to give you the distance that it went.
A to where? A to C?
A to B for this one, and then when you're doing it from A to C, you have to do all of that. I should have given you like it blocks this much energy on the way down, which is usually what happens.
There will be an NHS general meeting this Thursday, October 9th, in Miss Phillips Room.